Hello, my name is Yubin Lee, Yubin, and for my final project for EE531, I wish to look at two fairness papers. My research topic is not directly related to fairness. I currently am researching accelerators and computer architecture. So, I'm doing architecture research for um, AI workloads. Not just AI workloads. I'm also looking into robotics workloads. But I thought that if it were not for this project and this course, I wouldn't be able to take a look at what's going on in the fairness region. And because we have discussed fairness to some degree in the classes, in the lectures, and I am also interested in fairness. I wanted to look at two fairness papers. I really want to see how this research is being conducted. And when I look into computer architecture, I don't really see the implications of the research that I'm doing. But by looking at uh, fairness, I think that gives me a better understanding of the implications of the research that I do at my lab. Um, so I am going to do this presentation in English, although I am Korean, because I want to practice giving presentations in English. Um, so without further ado, I'll get started on the first paper that I want to discuss, which is called Generalized Demographic Parity for Group Fairness. It was published at ICLR 2022, and this paper talks about the metric of fairness for continuous attributes, continuous sensitive attributes. So demographic parity is a widely used metric for fairness, and this paper aims to generalize that. So the table of contents of my presentation is as follows. First, I will be talking about the background, and then the motivation of this paper, then the contributions. Then I will take a look into the algorithm that they propose, the metric if you will, which is the generalized demographic parity. And they give the formal definition, and then they give methods of estimating the GDP value. And then I will look into how they compared these two methods of estimating GDP. And finally, I will look into the relation that they show between GDP, generalized demographic parity, and adversarial debiasing. And finally, I will conclude and then move on to the second paper. So to give some background on fairness, machine learning models encode and sometimes they even amplify societal biases towards groups with different sensitive attributes. So it has been shown that sometimes there are models which exacerbate this biases. So when a model is trained, you will have inadvertently some um, sensitive metrics like their race, age, gender, weight, height, these kinds of metrics. And it has been shown that machine learning models encode these societal biases towards groups with different sensitive attributes. So they use these sensitive attributes and they are biased in their decision making due to these metrics, these sensitive metrics, sensitive attributes. And so this has led to the rise of the adoption of fairness metrics. And two of these metrics are demographic parity, DP, which was proposed by Feldman et al., and also the equal odds, EO metric, which was proposed by Hart et al. In 2016. And this paper aims to extend demographic parity, as I previously mentioned. However, in many cases, these individual sensitive attributes are unavailable and only aggregated attributes are available. What this means is that previously people didn't really think about these biases and made all the sensitive attributes about one individual available. But as people became more concerned about privacy, about these machine learning models being biased, these data sets now only provide aggregated attributes. So this leads to the necessity of requiring unbiased prediction over a neighborhood or a region level. So before there used to be individual sensitive attributes, and you could use these fairness metrics to find out, how biased the model is and try to steer away from that bias. But because now you have a neighborhood and region levels, there is a need to generalize these fairness metrics. And also, these sensitive attributes are inherently continuous. So DP deals with discrete sensitive attributes. But if we look at a lot of the sensitive attributes in our lives, like age, weight, height, these are continuous. They lie on a spectrum. So it is a bit difficult to use these fairness metrics required in fairness metrics defined in the discrete setting and applying it to a continuous attributes. So this paper addresses this problem. Continuous sensitive attributes require further metrics to be defined, and new methods for bias mitigation are required. But existing fairness metrics on continuous sensitive attributes rely on a statistical measurement of independence. So this paper gives two prior works. One is the HGR, maximal correlation coefficient, and the second is mutual information. And these rely on statistical measurement of independence. And the problem with that is that this measurement, these metrics, and the computation required that are computation intractable because of the involved functional optimization. So the big question that this paper attempts to answer is, can we extend DP for continuous attributes while preserving tractable computation? And as you might expect, the answer to this question is yes, and that's probably why this paper got published. So the contributions of this paper are as follows. There are the following three main contributions. The first is defining GDP, the generalized version of DP. They theoretically justify GDP via demonstrating the equivalence with DP for binary sensitive attributes. They provide the understanding of GDP from a probability perspective, and they demonstrate the connection between GDP regularizer and adversarial debiasing. Second is they propose two methods of estimation for GDP. One is histogram and the other is kernel. And they also prove that the kernel GDP estimation is better because it shows faster estimation error convergence with respect to the sample size. And this will be presented later on in my presentation. And also there is the experimental evaluation of GDP, and I won't be going over the evaluation part in this video, and I will be discussing that in the final report. So the proposed algorithm is called generalized demographic parity, which looks like this. And you can look at the paper for some details and figures. This is defined via the weighted total variation distance, where the weight for this is the probability density of continuous sensitive attributes. So this is just how regular DP. This is discussing fairness and regular DP. X is the inputs in RD. Labels Y are discrete, 0, 1, and we have a machine learning model F, which goes from RD to 0, 1, and it provides a prediction score, Y hat. And fairness requires Y hat to be independent of sensitive attribute S. Right? But this independence is difficult to optimize. So there are relaxed DP metrics to measure predictor bias for S in 0 or 1, so discrete. but DP cannot be applied for continuous sensitive attributes. So now we extend this to continuous spectrum. So S is now on a spectrum from 0 to 1 inclusive, and GDP is defined as the following: the expectation uh, of the absolute value of the difference between these two values. Now, the paper shows the relation between GDP and DP. The proof is in the paper. And they also show the connection of GDP and prediction weighted total variation distance, which is TV-pred in the equation, the second equation in this slide. And also the joint distribution, PSY hat, and the product marginal distribution, PS times PY hat. And it shows that GDP is a lower bound for prediction weighted total variation distance between the two distributions. The proof of this claim is in the paper, and this shows that GDP is a necessity for bias measurement. Now, the two methods of estimating GDP are histogram and kernel. So histogram estimation is given as this equation, and kernel estimation is given like so. The derivation for these estimations are given in the paper, but because of time's sake, I won't be going into all the proofs and the derivations. The paper also shows that for the histogram estimation, the error is big O of n to the minus 2/3, while for kernel, it is big O of n to the minus 4/5. So the proof of this is also in the paper, and they demonstrate that the kernel method for estimating GDP is better because it converges faster with respect to the sample size n. Also, they show the relation between GDP and adversarial debiasing, namely that GDP is bounded by the utility function with optimal adversary. As an equation, it is given like so. So to conclude, this paper proposes GDP, which is generalized DP, for continuous sensitive attributes while preserving tractable computation. This paper also discusses two methods of estimating GDP. One is histogram and the other is kernel. And they also show that kernel estimation is superior because there is a faster estimation error convergence rate with respect to the sample size. And because of time, as I said, I won't be discussing the methodology and evaluation in this video, but I will discuss that in the final report. The second paper I will be presenting for my final project is this paper. It's another fairness paper, and its title is On the Trade-off Between Robustness and Fairness. This was published in NeurIPS 2022, and this talks about adversarial training, AT, which is a common way to train models. And it also discusses the limitations and proposes a new method called FAT, fairer AT, AT being adversarial training. So the table of contents of my presentation for the second paper is as follows. So it has been shown that small and even imperceptible perturbations in a training set are sufficient to deceive DNN models, resulting in erroneous predictions. So these perturbations may be very, very small, almost imperceptible for humans to see. But these small changes in the input set, in the training sets, are sufficient to deceive DNN models, causing them to make wrong predictions or wrong answers to tasks that are given to them. And so adversarial training has been proposed to effectively improve robustness. So in natural training, the big R is risk. So the risk is defined as the minimum of the expected loss, as we have previously seen in the lectures. However, in adversarial training, the risk is defined as the expectation minimum of the expectation of the supremum of the loss. And this U is the perturbation set. And this has been added to the natural training so that adversarial training um, can be done on a model. So the model is more resilient to these perturbations of the input data in the training set. Now, it has been shown that models trained via AT perform well in some classes, but poorly in others. And that leads to some serious hidden dangers. So, for example, let's say you have a DNM model that needs to detect what is in front of it, and this is placed inside a autonomous vehicle. So, let's say that this model that is placed inside this autonomous vehicle was trained via AT. And this model, one example is that this model can detect cars, cyclists, trucks, buses, and those kinds of vehicles and other obstacles properly that are placed in front of it, but it cannot properly detect pedestrians. And obviously, this is going to be a very big problem. This paper shows experiments and also goes through the theoretical analysis in the paper. So I won't be going into detail, but it can be shown that these models trained via AT have differing performance based on the classes of tasks that they are given. And if we extend this to social ethics, then we know that, and we strive to have models that do not have discriminatory behaviors towards certain classes. So if these models trained via AT, because they perform well in some classes and poorly in others, if these classes are translated to, social groups, height, weight, things like that, then this becomes a fairness problem. And so there is a need to train models that are resilient to perturbations in the input data, but also perform well in all classes, not just well in some and poorly in others. So the big question that this paper aims to give an answer to is there a trade-off between average robustness and robust fairness? And more specifically, as the perturbation radius increases, will stronger adversarially trained models lead to a larger class-wise disparity of robust accuracy among different classes? The contributions of this paper is as follows. First of all, regarding the question that was poised, the authors of the paper claim that there is a trade-off between average robustness and robust fairness. More specifically, they say that as the perturbation radius increases, adversarial training improves the average robust accuracy of models over classes. But AT also leads to a larger variance of class-wise robust accuracy. And this paper goes through the experimental and theoretical validation of this claim, but I won't be going over those details and proofs in this presentation due to the time limits. I will try to discuss that in the final report. And this paper proposes FAT, which is a fairer version of AT adversarial training to mitigate this trade-off between robustness and fairness. So this is the algorithm proposed by the paper. I brought this straight from the paper because I didn't want to make mistakes if I rewrote this. So let the pairs x1, y1 to xn, yn be drawn IID from the unknown distribution D. So under appropriate conditions on the loss, parameter space theta with probability of at least 1 minus delta, the following holds for all theta in the set of possible parameters. The risk for adversarial training is bounded by the empirical risk plus the square root term and plus C over N, where VCAR of F is the variance of class-wise adversarial risk, and the adversarial risk and the empirical adversarial risk and the average adversarial risk are all defined as follows. The proof is available in the paper. So the goal is to minimize this adversarial risk plus lambda times VCAR. This lambda is a parameter that captures the trade-off between average robustness and robust fairness. And so now this becomes a minimization problem. And to facilitate computation of this minimization problem, first for the adversarial risk, they choose to use the empirical adversarial risk. And for VCAR, they use the following approximation, 1 over L times the sum of I equals 1 to L of the empirical adversarial risk minus the average empirical, the square difference. And so finally, the formulation of fairer AT is as follows. Minimize over F, R hat of adversarial, plus lambda times VCAR hat of F. So this paper also goes into the evaluation of how FAT is better than AT. Again, because of the issues with time, I won't be going into the evaluation, but I will be including them in the final report along with the data sets that they used and the methods and the results that they obtained. So to conclude, this paper first empirically finds the trade-off between average robustness and robust fairness. This paper also theoretically demonstrates that this is indeed the case. So they go both empirically with experiments and theoretically, mathematically, that average robustness and robust fairness, there is a trade-off between the two. And this paper proposes fairer AT, which is a novel method to mitigate this trade-off and also empirically evaluates FAT. So this concludes my video presentation of the two papers that I chose. And I know that I have missed out some points. The evaluation was not necessary in the video presentation, as I recall from the assignment guidelines. But in the final report, I'll be going into more detail into the algorithms and also discuss how these two papers were evaluated and the data sets and the metrics and all of those details. Thank you.